All right, so we're going to do an example problem looking at a variety of things in terms of forces and kinematics working together. So our problem reads, two blocks are connected by a string over a frictionless pulley. Block A is resting on a frictionless track, which is angled at 25 degrees with respect to the horizontal. Block B is hanging freely on the other side of the ramp on a pulley. The system is released from rest. How far does block A, the one on the ramp, travel in 3.5 seconds? So like with all of our processes, the first thing we want to think about is what are we interested in? What are we analyzing? The motion or the forces? What is the object that we're curious about? And as the problem reads, we want to know what block A is doing 3.5 seconds later. So we're going to first identify our object as block A. And I'm just at the border there of those words. So I'll pop down just a little bit. Okay, so block A is our object. That's what we go after first. We then ask ourselves, okay, well, am I dealing with motion? Am I dealing with forces? What am I dealing with here? It's asking how far does the block move in 3.5 seconds? Well, how far? That's a kind of a distance, displacement, position relationship. And so kinematics is really where I should be thinking in terms of going in my process. And so with kinematics, the first thing we think about is what really begins the motion, what's the initial condition, and that's when the block is released, and it ends, in this case at a time, what happens at the 3.5 seconds. So it ends at that 3.5 seconds, defines my final condition. So I gotta draw a picture. All right, so here's our ramp. Here's our 25 degrees. I have block A here on that ramp. Here we got a little pulley. And here's block B. And when we think of drawing a picture, we have to identify, of course, a few things. We need to identify the origin. I'm going to identify my origin here at x equal to 0 at the block A. So the origin is always x equals 0. I'm going to identify it at the location of A. And I'm going to say that my positive direction is up the ramp. Okay, so we're identifying the world. Where's the block located? Where's the origin located? And what's my coordinate system? Right, next step in our kinematic process is to list our known variables. So I'm only dealing with the motion of block A, that's what I care about. And so I'm going to think about, is this in 1 dimension or 2 dimensions? If it's in 2 dimensions, for our purposes, that's always been kind of projectile motion. It is moving up and to the right, but if I just orient my coordinate system like I drew with this pink arrow, if I orient my coordinate system up and down the ramp, this is 1-dimensional motion along the ramp. And so I only need my one list, and we're going to call that position X. So I have initial and final positions, initial and final velocities, acceleration, and time. So what's my initial position? Well, it's starting at the origin, so my initial position is indeed going to be 0. Don't know my final position, not part of the problem that's been given. My initial velocity, it says it starts from rest, so that's going to be at 0 meters per second. Don't know how fast it's going when it ends. Don't know what the acceleration is. Oops, I'll put that as a question mark. But I do know that the time of my motion that I care about is 3.5 seconds. So the question is asking how far, and how far is going to be information about final position. So final position is what I am interested in. When I think about my kinematics equations, final position is in a couple of them. And the one that I think is going to serve me the best is the one relating to initial velocity and acceleration and time, because I have time. The other one, final position, is, remember, doesn't have time, but it requires me to know my difference in velocities, which I don't. So I'm going to use the one with time. So x final we don't know, so that we keep that as its variable. X initial is 0, v initial is 0, time is 3.5, plus 1/2 acceleration times 3.5 squared. So if I simplify this, I find that x final is equal to 6.125 times a which tells me I need acceleration in order to answer this question. So this is what I'm going after. I need acceleration. What's that acceleration of? That's the acceleration of block A. This is all on block A. Well, if I look at my list, I can't get acceleration from anything there. So we know that when I need acceleration, I can't get it from kinematics. My strategy is to go look for it in forces. So we're going to do a force analysis on block A. We've already identified the object. Our next step is that free body diagram interaction process. So we're going to do a free body diagram on block A. And we want to think about those interactions in order to generate that free body diagram. So what's interacting with block A? Well, we have the force of gravity interacting with block A. And that is between block A and the Earth. How does it look? Well, as I put my free body diagram together, the force of gravity always acts in the straight down Earth reference frame. And we know the force of gravity is equal to mg. So I always like to put that mg in there right away so that I don't forget. All right, what is the next force? What are the other interactions? Well, it's interacting with the ramp. It's sitting on the ramp. So we're going to call that the normal force because it's because of that contact. That's block A and the ramp. And the normal force acts perpendicular to the point of contact. So it's kind of going to be up and to the right here. There's my normal force N. Then we have the string. That's interacting. We'll call that a tension. That's between the ramp, the string, the rope, let's just say, and block A. And it's pulling up the ramp. So it's kind of going in that direction. So here are my three forces acting on block A. Number those forces, and we break them up into their horizontal and vertical components. So here is force 1, 2, and 3. Now, because I have defined the world for block A as being along that ramp, my horizontal and vertical are shifted, they're rotated. So we think of this often in our force analysis as horizontal prime, vertical prime. So we have horizontal prime and vertical prime, that's that rotated axis. We can draw that axis on there for some clarity. So this is what we're referring to in terms of our axes of motion analysis. So forces 1, 2, and 3. Force 1, the force of gravity. Well, that is acting in components in our horizontal prime and our vertical prime. So horizontally, it's pointing in the downward direction. It's our horizontal component like this. So we have minus mg cosine of the angle. You can look at that angle analysis and see that that's the cosine of the angle, the component, along the horizontal direction. And, sorry, not the cosine, the sine. Good griefing. Component along the horizontal direction is the sine of the angle. Here's our angle of 25, so here's 25 degrees. That makes this 25, opposite sine. Sine. Vertically, it's pointing in the negative direction again, so that's minus mg, and it's the sine. 31 again, getting ahead of myself. This is why it's always good to check these. Cosine of the angle. All right. Force number 2 lies along our horizontal prime, and there's nothing in the vertical component. Force number 3, there's nothing horizontal. It's only in the vertical component, and it points up in the direction of our system. Okay, next step is to sum the forces. We are interested in the acceleration in the horizontal direction. So I'm going to just start with that. We'll see if we need the vertical. So the sum of the forces in the horizontal direction is equal to the mass times the acceleration in the horizontal direction. And that's why I went after this. So this acceleration is what we're talking about. So we're going to start there. So that equals T minus mg sine of theta equals the mass times the horizontal acceleration. And what does that tell me? Well, I have the mass. I don't have the acceleration. That's what I was going after. I don't have the tension. So in order for me to solve this problem, I need T. All right, so I needed A, now I need T. Can I get T vertically? It's not involved in the vertical direction, so I don't even have to analyze the vertical at this point. Okay, so I need T. And what else is T related to? Well, T is also related to block B because that rope is interacting with block B, and therefore the tension is interacting with block B. So because I need T, I'm going to go and analyze block B. Tension is a force, so I'm going to do a force analysis on block B. So we're going to start with a free body diagram of block B. That requires me to do both that interaction and the free body diagram at the same time. We know there's a force of gravity on block B between block B and the earth. That always points earth vertical. So if I go to my free body diagram, I'm going to see that there is a earth vertical line on that free body diagram. And then the tension, okay? So we also have the interaction of the rope. That's between block B and the rope. And that points in the upward direction. Kind of got in there. I'm just going to erase that a little bit. There we go. There's our tension T in the upward direction. All right, anything else? Not so much. So we are now dealing just in the vertical plane for these forces, so we only have to analyze the vertical. It is the true vertical, so we don't have to do any rotation. So we'll separate our forces into their vertical components. So we have force 1 and force 2, but we're reiterating the process here. Force 1 is minus mg, and force 2 is, of course, our tension. Continuing on, we know that the sum of the forces in the vertical direction is going to equal the mass times the acceleration in the vertical direction. It's going to move up and down, so there is an acceleration. And so we have T minus mg is equal to the mass times the acceleration. Now this is a really good time to pause and think about our letters that we're dealing with, and we want to be careful about them. So this is a great time to say, all right, wait a minute. I am dealing with two different objects here. They both have masses. They both have accelerations. I need to make sure I'm clarifying which is which. And so when dealing with A, this is the mass of A. So we really have the tension, I mean, we've always had this, times the mass of A, g sine theta, equals the mass of A times the acceleration of A. So we're going to put that in for clarity. In our object block B, this is the tension minus the mass of B times g is equal to the mass of B times the acceleration of B. All right, so I want to make sure we're very, very clear about which objects we're dealing with. Now, we've already talked about these tensions being equal, and which is why I went after T. This is meant to give me that tension, but well, now I've introduced this acceleration of B, which I'm not given in the problem. But these two objects are interacting, they're influencing each other. They're moving together. So what do we recognize about the acceleration of mass A and the acceleration of mass B? Well, they have to be the same. They're moving together. They're accelerating together. But we want to be careful of direction. Because I've identified gravity in block B as pointing in the downward direction, and I identified it as negative. Downward is negative, and this block indeed is going to move in the negative direction. A's block is moving up the ramp. That's positive. So although they're moving together by the definition I have chosen, which is convention, they're moving in opposite directions. So we have to be careful and aware of that. You get to choose your direction. So you could have chosen a different direction, in which case then they would be the same. But you just want to be careful that you're paying attention to that. So we have the acceleration, what I'm going to put down here for us to know is the acceleration of A is equal to, in magnitude, the acceleration of B but it's actually in the opposite direction based on the coordinate systems I have chosen. Okay. Now I have one equation with two unknowns and another equation with those same two unknowns. And I'll make sure that's crystal clear by substituting the acceleration of A in this equation. So we end up with T equals the mass of, oops, I'm not going to jump steps on you. T minus the mass of B times G is equal to the mass of B times minus the acceleration of A. So that's where my negative comes in. Okay, now I have two equations, two unknowns. I can do something with that. I can do math on that. I got that, all right? So I'm going to solve both of these for T because I'm interested in solving for A, so I want to keep that with me. So in this case, I have T is equal to the mass of A times the acceleration of A plus the mass of A G sine theta. And here I have T equals the mass of B negative times the acceleration of A plus the mass of B times G. Okay? All right. So now I have two equations with T in them. So I am going to set these two equal to each other. I have mass of A, acceleration of A, plus the mass of A, G sine theta, is equal to the mass of B. No, I'm going to get that negative in front because we're often used to seeing it that way. Minus the mass of B, acceleration of A, plus the mass of B times G. Okay? So all I did was set these two equations equal to each other. Now I have everything with just A left over. Now, like I've shared with you multiple times, you can solve this and certainly then plug in numbers later. I'm kind of a numbers girl, so I like to put numbers in. So I have 7, mass of A is 7, so I have 7, just want to make sure I have my right mass, times the acceleration of A, plus 7 times 9.8 times the sine of 25 equals 4, negative, 4 times the acceleration of A, plus 4 times 9.8. All right, combining like terms and all that good stuff, we end up with the acceleration of A equaling 0.928 meters per second squared. That, my friends, is the acceleration we want to put back in here. And when we do that, we find that x final is equal to 6.125 times 0.928, which equals 5.68 meters. Toot, 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 toot. All right, I'm going to pop this over here. Put that back in there. We have x final, just so you can see it better. 6.125 times 0.928. X final is equal to 5.68 meters. All right, so fun, okay? So, really letting the physics take you where it needs to take you. Starting with what you're interested in, tackling it. I want motion, I'm doing kinematics. Recognizing that, well, if I do kinematics, I need acceleration. How do I get acceleration? Forces. So I do a force analysis on the object I'm interested in. Recognizing I need something. Okay, what else is it related to? Well, it's related to that other block, force analysis on that, and then the physics is over. Now we're just doing a little bit of algebra. Recognizing, of course, this key point. All right, nice work. Long problem, lots of fun. Good job.